So, welcome back to the last session on advanced algorithms. Let me go back a few slides because last time we started discussing the theory of inapproximability, showing that certain problems cannot be approximated better than something or not at all in a certain sense. And the first definition in that respect that was tailored to this topic was that of a gap problem, which is a decision version of an optimization problem, where we exclude certain instances, namely those that fall into a gap. So we defined two values here, and to be precise, we had this part excluded and this part included. But this is not often not important. And we only allowed instances that are to the left or to the right of this gap. The definition of this was we take the optimal objective value of the instance and divide by the size of the instance. I said it last time, but I want to stress it again because it occurs here in more specific examples all over the place. That I would like to interpret this size of the input a bit more liberally than fixing the length in the number of symbols in some encoding, because this is very inconvenient. What we will do is interpret this as the size that makes sense for the problem at hand. For example, for 3-sat, we take the number of clauses as the size of the instance. You can always make assumptions about the variables and their names, that they are constrained to numbers in 1 to m. You can't have more variables than clauses, for example, or, well, not more than 3m variables if you have m clauses and so on. So these are certainly related, but it's much more convenient to talk about the fraction of clauses that are satisfiable. And for other problems like independent set that will come up later, we'll take the number of nodes. There it's a tiny bit more questionable because the input length will also depend on the number of edges, which might be a good bit larger than the number of nodes. But again, what we're interested here in is a gap for what we defined as the ratio of approximation. But here we only have the optimal value, and we have to make it somehow scale with the scale of the problem. So remember, here we are counting things, clauses and nodes, and both go to infinity if we increase the input sizes, in a certain sense at least. For independent set, we might make the input infinitely large and still have less nodes than the length, but still they have to grow for interesting instances. So it's only meant to be a scaling so that we have a gap that remains stable. I think in all the examples it will be quite clear what this is about. And that also means if we talk here about the impossibility to have a certain approximation algorithm, a certain guarantee, then this should be in the numbers that we're used to work with. And these were fractions of things that work. It's, for an approximation algorithm, we had the actual solution and the optimal solution that we set in relation. Okay. And then for the reductions, the same holds. Now these gap reductions are a bit more involved because they have all these parameters. So I thought it would be nice to have at least a few simple examples of how such a gap reduction can look like. And the first one is we take max 3-sat, so we have optimization problems. For the gap reduction, talks about the optimization problems. And we have a certain gap that we translate from one problem to another. Another remark is here I only talk about the maximization problems. And I had the same remark here for for the gap problems as well. You can do the similar definitions for min. Then for the gap reductions, you have all combinations of min and max. Because we have to flip the meaning of yes and no, otherwise we get in trouble with NP versus co-NP. I guess that's clear. It's not really anything that's complicated, it's just technically you have to distinguish the cases, otherwise the theory doesn't work. So for my examples, I just pick maximization problems so that we don't have to deal with that. Okay, the theorem, well, this lemma here says we can actually choose the gap at will as we would like it. And then we can take any max 3 set instance and turn it into an independent set instance, which also has a gap, but the gap is a bit shifted or scaled. And the reason why this happens is that we have a certain blow up in the reduction. So first of all, we assume that every clause has exactly 3 literals. But I don't insist on having 3 disjoint ones or 3 different ones. So we can just duplicate some literals if there's less than 3 in any of the clauses. And then we use the same reduction as we would in the ordinary polynomial time reductions. And we just have to look a bit closer to see that it's actually a gap reduction. So we've done the same thing, essentially the same thing. The graph that I used there is slightly different, but the core idea is the same. We use the same for the vertex cover problem, and vertex cover and independent set are for vertex cover. They are related because the complement set of nodes. If I have an independent set, I can take all other nodes, then they are a vertex cover and vice versa. So it makes sense that a similar reduction shows up here. So if we have a clause with 3 literals, then we make a node for each of these and connect this as a triangle. Two, 3. And we have such a triangle for every of the clauses. And additionally, we have certain edges between the clauses whenever these contradict each other. So we're taking an instance of 3 set and we would like to construct an independent set instance. So that means we would like assignments of the variables to correspond in some sense to an independent set. And what we will have is that we connect nodes that contradict, so they should not be part of the same independent set, because they're not independent. And say here another one. So this is, I guess, the general construction would be easy to write down. I'll spare you these details. Now the assignments in the formula for the variables, if that satisfies k clauses, they now correspond to a selection of nodes where we pick 1 vertex per triangle. And there's a subset among these selected nodes of k nodes that is independent. Okay. So whenever we want to satisfy the formula, we have to satisfy all the clauses. That is, we pick 1 node from every of these triangles. And in an assignment that satisfies all of phi, we would have to have that the whole collection is an independent set, so that I have no contradictions. Now, if the formula is not completely satisfiable, but only has k satisfiable clauses, or if I have just any assignment that only satisfies a certain number of clauses, then if I mark the corresponding nodes in the graph by picking one of these in the triangle, if there's more than one satisfied, then I have some choices. But there's always a selection so that I have a k independent subset. And this in particular holds for the optimal assignment, so the assignment that satisfies the most clauses. And I can make this gap distinction if the number of satisfied clauses divided by the number of all clauses in the formula is greater than C or less than S. That's what we assume by using these gap parameters. Now we just leave C and S as symbolic values. Then you can check that you use k nodes in the graph that are independent, but you have 3m nodes in the graph in total. Well, and then you just get the translation that then the gap is a bit scaled. Okay. So often, or well, for nice problems, these gap reductions are actually quite simple. You just have to find a reduction that has this close connection between the two problems, then it's simple. In general, it might be tough to find ones because a lot of the reductions that we have actually do not translate gaps in this sense. In particular, if you look at the Cook reductions, how you translate any NP problem to a general set formula, these tend to be very sensitive to small changes. And that means that in the set formula that you get from this general reduction, it could be that there's just a single clause that's not satisfied by instances that are no instances. And so by growing sizes, there's no gap that you can retain. But in this example, it worked fine. And there's another example that's not much harder, but interesting from another perspective. And that's the self-reduction from independent set back to itself. And, well, this might be a bit tough to see. You square the gap, which means, so the interesting part was C divided by S is the approximation ratio that you exclude if these gap problems are hard. Okay? So what this means is that if you have a C divided by S approximation excluded, then with this reduction, you see that there's also no C divided by S squared reduction. And because C divided by S is greater than 1, this is larger. So that's why you have this corollary. Either there is an approximation ratio of any guarantee, or there's no fixed ratio approximation at all with constant approximation ratio. Because essentially you can use these sizes a constant number of time to get to any fixed number. As we will see, the reduction is not sufficient to show stronger results. In particular, you cannot decide which of the two holds based on that reduction, because there's an immense blow up in the size of the instance, so you can't use it more than a constant number of times, say. Okay, the reduction is actually relatively simple, but a bit ingenious, if you like all good reductions are. The idea is you construct something that you might call the square graph. So you start with some graph, and well, maybe I just give you an example, and then you can decide whether you would like to see the general construction. So this is G, and now I need 4 identical copies, and that's not the way to go. I have to move them immediately. And I align them so that they form the same graph again. Or maybe the better way is I start with that graph and replace each node by a copy of the graph itself. And then in that copy here, I have these additional edges, and these are just connecting all the vertices with all the vertices here. So completely connected, right? I will not draw all of them except for this, well, contracted picture in a sense. Now, if you consider the maximal independent set in this graph, it's a simple example, so you can pick these. Then the maximal independent set in the square graph is in each of the nodes that were independent here, you go into the inserted graph, and they're marked the same red nodes as in the small graph. So in a sense, you mark this big node, and this big node, and this big node, and then zoom in and mark the small ones. So it's obvious that these are independent because they are independent inside and outside, just by definition. Is that clear? Would you like to have the formal construction? I mean, it's like you take literally the square of the nodes, and the edges connect nodes like this. So it's set. And these are connected if either x prime was an edge or y prime was an edge. Well, or both. Okay, then we should count the sizes. So we have k divided n in the original graph. And then again, we ask, is that greater equal than c or less than s? And now in the translated graph, we just have the square of both things. And we ask the same question. And then, of course, we also have to square the other side of the inequality, right? And that's how you get this amplified gap. So I think the picture is pretty nice, and the
definition is correct.
I hope so. So I mean, each of these nodes has an inner and an outer vertex in the original graph.
Yeah, but if I have two of the smaller nodes that are not in the same.
Oh, you're right. Yeah, you're right. That's not enough.
The second one has to be x equals x prime and
okay, we should say which is the outer, which is the inner. Yeah, that's it. It's asymmetric, right? If the outer is the same and the inners are connected, then I connect those. And if the outers are connected, I connect them no matter what happens inside. You're right. Okay, so we've seen there are nice examples of gap reductions. And in fact, already last time I showed you that for bin packing, you can argue that there can't be something better than a 3/2 approximation, because we could reduce the partition problem, which is NP complete, to bin packing. And we noted that in that reduction, you only produce instances that have either 2 bins, which is then optimal, or 3 or more bins. And a 3/2 approximation allows you to distinguish between these two cases. So you could now go ahead and try to find reductions using bin packing as the basic problem. So reduce stuff to bin packing and try to find a gap reduction there. Unfortunately, I couldn't find a nice example of such a reduction. And it might be that bin packing is just a very unhelpful example of a problem to start with. Whereas for the usual NP theory, we are used to reduce stuff to SAT or 3-SAT. So it would be great to have a similar result for SAT. But as I said, the usual Cook reductions don't give you anything like this. They are not gap reductions. They shrink the gap to basically nothing. And therefore, people have found a very interesting theory that's kind of philosophically interesting on its own right. I will make a comment on that, see frowns on your faces, after the definition. And in the end, it will turn out to give us a proof that 3-SAT can't be approximated to arbitrary precision. And then this serves as a starting point for further reductions, but we won't have time to go into these anymore. So the theory is called probabilistically checkable proof systems. And the philosophical part is about a very strange notion of proof, of mathematical proof. But the first version is just about computation and definition. So we define something that's called a probabilistic verifier. You remember we started, when we talked about NP in this course, we started with the equivalence to VP, the problems that have a polytime verifier. So we're given the instance, and on top of that, a certificate, and we have to check whether this certificate shows that X is in the language or not. And the nondeterminism, that is the usual definition for NP, is essentially used to create a random, or well, to non-deterministically generate a certificate. The point was that for words in the language, we had to find one certificate, whereas for words not in the language, all potential certificates must be rejected. And we will now generalize this notion of acceptance a bit and throw in randomization. So it's also a nice finish for our course, because several ideas from all over the place come together here and create a new kind of interesting theory. So randomized algorithm V is a probabilistic verifier for a certain language, but it's not a usual Turing machine in the sense that we usually had in the we discussed it in detail in the beginning of the course. It additionally has a random access tape where you can, if you like, you can imagine there's an additional address tape, and you write the binary number of the cell of the proof that you would like to read into that address tape. And what you get back is then 1 bit of the proof string. So the proof string plays the role of the certificate. The reason is just that these probabilistic verifiers come from a different part of TCS, and therefore people tended to stick with the term proof instead of certificate, but it's really the same concept. So we have this strange machine that usually has to compute like a Turing machine, but whenever it accesses the proof, it can use any position inside the proof string without having to go there. And the reason will be that in the end we will have to be very scarce with our accesses to the proof string. From that perspective, that's why we need this random access. Otherwise, it would not make a lot of sense because the running time is not critically affected by that. Okay, a probabilistic verifier has to run in poly time. That's just the usual idea of efficiency. And we use the input size as usual to measure the running time. And just to stress that a third time, we assume that this random access to this proof string has a constant running time. It's like an oracle. Is that a question? You're just thinking.
I'm not sure why we actually need the random access, because if in every step we actually have to linearly move the tape to the position where we want, because it's just a factor of n more. So we're still in
yeah, so your question was why we need this constant time random access thingy. The point is that in the end, we will use proof strings that are exponentially long, at least in some examples. And this is fine with random access as long as you don't try to read all of the proof. And that's the critically different thing in PCP systems. It's proofs that are horribly long, not wrong. They are horribly long and not intended to be read entirely. Maybe a lot of our proofs are written like this, but they actually shouldn't. The usual notion of a mathematical proof has to be followed from the beginning to the end to verify it. And this will be about proofs where you verify locally just a few bits, and then you can use that already to conclude something. And what can you conclude? That's the points 2 and 3 that I didn't talk about yet. For every word in the language, there must be some certificate so that we always accept, and always now is with respect to the randomness that this verifier uses. So it's a Turing machine with a lot of tapes. There's an input tape. We might just use this as the usual work tape and input tape combined. So X and work tape. So this is machine V. Then there's a tape with random bits. These are read-only. That's just probabilistic Turing machines that we've talked about before. And then there's this extremely long proof pi with, I don't know how to draw this. What's random access? I don't know. Maybe some magnification glasses or... Okay, let me stop it at this point. To use that, we have a small address tape. So the idea is you write the address that you would like to read into that tape, and then, well, this moves and jumps to the right position and gives you the bit back. Okay. Is this model of computation clear, no matter how strange it may seem? To make things a bit more confusing, just because it's like this, here I didn't mention the second part, sorry. So we have to surely accept every word that's in the language when it comes with the right certificate. This is as it was for non-deterministic polynomial time Turing machines. We have to accept the correct input if I give you the correct certificate. If I have an input that's not a language, then for all certificates, I must reject it. But here we allow a certain error. We only need to reject it with probability 1/2. And we had something very similar for randomized algorithms, the one-sided error Monte Carlo methods for decision problems. But they were exactly the other way around. We had to, for sure, detect something that's not in the language. And something that is in the language we might fail to recognize half of the times. So just be aware of this complement here. Okay. Well, on top of that, this also has a certificate, whereas, of course, these algorithms don't get a certificate. These are just randomized algorithms. It's a bit mind-bugging, I agree. And here's the second definition that we need, and then that's it for the moment.
We also defined the little L up there, like at the end of the where ln is.
Oh, yeah, right. The proof string has a certain length bound. And this is actually a crucial thing. So we didn't need the certificates in VP to be bounded in a sense because we could only read a certain part because we couldn't jump. But with this random access, we could have huge proof strings. And we could just jump to any position that we'd like. And therefore, the length of the proof string is bounded by something that's absolutely not defined here. I think this belongs to the next definition, and I just inserted it into the wrong place, which you also... Okay, let's take this. I can't cut and paste in the slides, unfortunately. This belongs here. Let me see if we can... Oh, dear. Let me just move this down. Xornal has some limitations. There will be a restriction on the length of the proof, but not at this point necessarily. But now in the really useful definition, we define a probabilistically checkable proof system. And this has two parameters that have to do with the size of the proofs, namely R and Q. And the idea is you can memorize this. It's randomized queries. That's why it's RQ, not QR. Okay, maybe it doesn't help you. So these are two functions. And then PCP RQ is a class of languages, namely those for which we have a probabilistic verifier as we defined it. But now we restrict its usage of certain things. It can only use R of n random bits, or O of R of n. And it can only inspect a certain number of bits in the proof. Okay? And we would like to restrict the length of the proof in a sense to all the different positions that we can ever access. Because if I have only R of n random bits, there's only 2 to the R of n different random computations. And in each of those, I can read Q of n bits. So this is about the number of bits I can access. But, of course, usually a verifier, the bits that a verifier accesses depends on the input x. And x does not occur in here. So even though in many of the books that I checked for this topic, it says like, oh, this is essentially a void restriction because we can't read more different bits than this anyway. I think this is plain wrong because you have to let your verifier make its choices dependent on the input. Otherwise, that would be gross. That doesn't make a lot of sense. And if you then don't restrict the length of the proof at all, you could do a very simple trick. You can just assume that your proof enumerates all possible instances for the problem. And then you just translate your input instance into a number, which only has to be polynomially restricted. Could be a huge number, right? And then you access the proof bit at this position and check whether it's a yes or a no instance. So that would give you trivial PCP systems that don't make any sense because you can't possibly generate these proof strings. And they're not useful for what we will do in later on. So it makes sense to exclude these by definition. And interestingly, all the books do have this size restriction in the definition. You just comment on that and say, well, it's actually not something to worry about. You should worry. You should definitely keep this in mind. Okay. One last thing is, it's a technical convenience to assume non-adaptive verifiers, where these Q positions that the verifier reads depend only on the input and on the random bits, but not on what you read from the proof string. Okay? So you can imagine that this might be restrictive or not, but apparently it's possible to show all the theorems that we use about the PCP theory in this non-adaptive setting. Is the difference clear? Okay, it's something to go over again in a bit of detail, but let me give you just the trivial examples. If we use a probabilistic verifier that doesn't use any random bits and doesn't read anything from the certificate, then we're back to a plain polytime Turing machine. So we get the class P. Okay, that was super easy. If you use a probabilistic verifier and don't use any randomness, but allow it to use a polynomial number of bits in the proof string, then we just retain VP in that, and that means NP. That's also trivial. In particular, this acceptance condition, if I don't use any kind of randomness, then these must be just 0 or 1. And then we're back to the non-deterministic case. The third example, that's a bit less trivial in a sense. If I make use of randomness, polynomial number of random bits, but I don't read the certificate actually, well, then I can do whatever a randomized algorithm can do. And because we have this flipped kind of acceptance criterion, it's the class co-RP that we retain. So it's the set of all languages so that we have a one-sided error Monte Carlo method for the complement. Okay, these are boring examples because there used to be a 0 in one of these places. Maybe we can have one more interesting PCP system. And I'd like to show you one for 3 set that uses n log n or O of n log n random bits and O of n accesses to a proof string. Okay. The idea is, okay, first let's just fix notation. We have a formula given with m clauses and n variables. So I'll use n and m inside the proof. Here the n is actually the input size, if you like, but since the number of variables and the number of clauses are essentially bounded by that, it doesn't make a very big difference. I just wouldn't want to change the names here on the fly. So the idea is that pi, the proof or the certificate, contains a satisfying assignment. And encoded in the trivial way, you just write in the increasing index order of the variables, whether they are 0 or 1. Well, it contains a satisfying assignment if there is one. Of course, if x is not satisfiable, the phi is not satisfiable, then we can just have any random thing in this pi. But this is not actually something we don't have to worry about. In the case that it's a no instance, we have to live with all possible proofs anyway. Yes?
So pi has to contain a position that is 1, where if an assignment exists, then the random access to this position with address assignment would be 1, right? That's what the top means.
I'm not sure I got the question, but let me just elaborate what I mean with that. That's maybe easy. So pi has pi 1 up to pi n are just the bits in pi in the string. and we say pi I is the same as the assignment of variable I, which is a 0 or a 1. And this is a satisfying assignment if one exists, or otherwise some random whatever. Is it clear now? Okay, okay, let me just first explain how this works. Now we take the following algorithm. Oh, this will actually be our verifier. We choose a random clause from our input. Then we access the corresponding bits. Okay, I'm a bit sloppy here. These are literals, and these should be the indices of the variables. And we simply return whether C is satisfied. So it's a very simple algorithm. So why should that work? The point is this does not yet work completely as we would like it. If phi is satisfiable, then for the correct proof string, let's call this A. I'm sorry, there will be a B in a second. So if we have there's no X, phi and pi with the correct certificate, then we accept for sure, because that's just the satisfying assignment and any clause is satisfied under this. But if phi is not satisfiable, then no matter what proof string we input, there is one clause at least that's not satisfied under this assignment. That's the definition of unsatisfiable. And that means the probability that our algorithm picks this one clause that's not satisfied is at least 1 over m, 1 over the number of clauses. This is about the right form for a probabilistic verifier. It's just the probability is too low, so let's amplify that. We know how to do that. We repeat A a certain number of times. I'll tell you in a second how often. And we return 0 if any of the runs return 0. Because in case we should return a 1, all of the runs must return 1. So whenever we see a 0, we know that we're in the unsatisfiable case. So now again, if phi is satisfiable, we have the same result. Because A must have the same result in all the k iterations. If phi is not satisfiable, the probability that this goes wrong well, we can express that by the counter probability that actually it's the counter probability that A returns 1 all the times, even though that was the incorrect result. Okay. And then we insert. And we should have that this is 1/2. And then you can solve for k. And what you find, this is, well, you just move that to the other side and take logarithms. It's not really complicated. So this is m minus 1 over m. And then on the other side, you have 1/2. So for all k that have this, that satisfy this, you could do that. then using logarithm rules, this is minus log 2, where now log is, I'm undecided what base I should use. I think it doesn't matter. Let's take ln, because I divide by the same log. So it's log of this, and because it's a number between 0 and 1, I can take the to the minus 1 out. And then divided by log of this, and log of this is the difference between log of m minus 1 and log m. Okay. Then you see if we flip the signs on both in both parts of the fraction, then we get back to a nice positive number. And now the point is that the difference between the logarithms is essentially 1 over m, because the logarithm is essentially the harmonic numbers with a bit of an error. And the difference between two harmonic numbers is just this one fraction, the last one that's missing. That's an easy way to memorize that. You can show that it's in fact asymptotically equal, or, okay, let me write it down. So this is asymptotically equal to 1 over m in the first order asymptotic. And you can actually show that it's always smaller. So if we show that k is greater than this, then it's also greater than this, which is what it should be. Okay, I might have written this in a nicer way, but what kind of, so it's ln, I'm sorry. Here I use that this is ln for the harmonic numbers. Okay, if I choose k like this, then this works out. So we need a logarithmic number of repetitions until we get the desired probability. Sorry, not a logarithmic, a linear. So this is ln2 times m. We need a linear number of repetitions, which in a sense means that we probably checked every single clause in our super cool randomized verifier, right? And if you sum up, then over all of the runs, okay, now n is again the input size. Should I write q of m? Would you like that better? We can write size of phi. That's maybe better. So we need a linear number of bits that we read, because in every repetition we read 3 bits. So 3 times size bits. And the number of random bits that we consume, well, that's something we didn't discuss for A. It has to choose one of the m clauses. So let's say this is log m bits. We know that we can't really perfectly sample here. We just ignore that tiny difference, I think. Or we just error to the right side. So for all the parts that we would actually do rejection sampling, we can just output 1. And then we get a slightly less probability here. But we can correct for that by doing a few more repetitions. It's doable, even though I've been again a bit sloppy. Okay, question.
You are using the probability that the algorithm alpha of phi and pi is equal to 1. If you just scroll up, you can see that
This one?
is 1. Yeah, exactly that one, yeah. And if we scroll up, that is in the algorithm is just 1, so it seems a bit...
No, it's 1 in the case that the formula is satisfiable. But you're in the case that it's not satisfiable. And then it's the counter probability of this thing. Is that clear? So these are two cases. And we have the same cases here again. And we're in the second one. Okay, so I don't know whether or not you're impressed by this super cool. Yes, another problem?
If we allow n queries to the proof, why do we use any randomization at all?
That's the right question. If we use n queries to the proof, we can read the whole proof. So why randomize it all?
Yeah, we could have shown
Yes.
is a CNP of 0 n, and would be
Yes.
shorter proof.
You're right. So for 3 set, I can't write this. So no. Because, okay, one would work. I have to do one dummy random bit, otherwise the proof length is restricted. Remember that pickiness in the definition. But you're right. The proof system I showed you has the merit that it's using randomization and so on, but it's actually not making any profit from that. 1 and n would just work because our proof has length n. So this is fine. It's just that this doesn't help at all because actually it's the same certificate as we used for non-deterministic machines. So it's actually, in hindsight, it's no wonder at all that we didn't need randomization. Okay? I decided to not do it. We could improve this a bit by, in each step, choosing a set of p clauses and forcing the proof to contain 1 bit for every subset of p clauses. That blows up the proof by a certain factor and reduces the number of queries we need by a certain factor, and also reduces the number of repetitions that we need by a certain factor. But it turns out this all doesn't really help so much. But if you do it to the extreme, if you, okay, we can, so this, here the proof is very simple, so I'll just, don't forget what I said. I'll come back to that in a second. So here we do something very boring. We assume our proof just has pre-computed all formulas that are possible. If I fix the number of clauses and variables, this is certainly some bounded number. And in fact, we can encode every formula, well, in some canonical way. Okay, let me do a very boring example. You could just say I start always with a 1. Then here's no not, so that's a 0. And then I need numbers up to 3, so that would be 0, 1 for 1. Again, no not, 2 becomes 0, 1, 0. And then you have a not and this. So this could be a code word for this formula. And so, in a sense, we showed that I don't need more than, so for the number of variables, something like this, to encode the index of the variable, 1 for whether or not there's a negation, and this for all the clauses. That's the length of the code word for one clause, and that's also the exponent of 2 for the number of different such formulas. And this is just m log m. So if I allow my proof to have 2 to that many, so the length actually is what what I need, 2 to the m log m, with now the O up here, so that's a bit ugly. Let's just do it here, even though I don't like that too much. If you allow such long proofs, then your proof can just contain pre-computed all possible instances, and your algorithm just computes this code word and accesses the solution. Maybe this example is very boring, but it shows you that there certainly are locally testable proofs for certain things if the proof just contains the truth of everything. It's just not a proof in a sense that would give us any kind of insight. And that's also the reason here this R only has to be chosen so that it allows this length of the proof, but we actually don't use any kind of randomization. So we can play with these parameters of PCP, and we can even make only a constant number of checks, even just a single bit from the proof, and we can certify certain instances with that. But as long as we have a blow up here like this will not be a lot of helpful insight. So the question would be what to do with these things. What can we do with such PCP systems at all? And one thing we can do if we have a PCP system, a verifier that uses R of m random bits, Q of n proof queries, and has a running time P of n, because it can do more things than just querying bits, right? So we need an additional bound. We assume this is a polynomial, that's in the definition. Then we can actually simulate this proof system by a non-deterministic Turing machine with the following running time. It's exponential in the R, but just linear in the other terms. And the proof is essentially, we just describe how you would do this, but it's simple. You non-deterministically guess pi, which has exactly the length L, where L is 2 to the R times Q. That was the length that we allowed. And you can do that in this running time, 2 to the R times Q. You can generate this proof string. And then you de-randomize the verifier V by just running all its potential random runs sequentially, one after another. So run all 2 to the R, it's not more than those. I'll just skip the of n. Well, and if you think about it for a second, okay, each has running time P of n. And when should you accept? Well, when all of these accept. Because then you're in the case that there's this probability 1 to accept, then you have the right proof, otherwise you just reject. So in general, a running time of a non-deterministic machine with an exponential part seems like not very helpful. If you have only a logarithmic number here, well, and actually this could be larger, but let's leave it like this, then you obtain nothing more than NP. Okay, because, well, 2 to the log n is just polynomial. Even if we allow, so this here is an O of log n actually. It could be some constant times log n, but then 2 to the constant log n is still n to the constant, to some constant. Right. So that's one thing. You can simulate some PCP systems, but you need quite restrictive parameters here. And another direction is you can translate a PCP system back to a formula and to a very specific one. So if you have a PCP verifier V for some language, And again, we assume it uses R random bits, Q proof queries. Then by we can construct, I mean there is an algorithm with a running time that is essentially depending on the length of the formula. It doesn't have to do any magic steps. So we can construct a formula, a Boolean formula phi. That's actually in CNF. With this size and the following nice property. If a word is in the language, then the formula we construct is satisfiable. And if the word is not in the language, the formula is not only unsatisfiable, in fact, the maximal fraction of clauses that we can satisfy is bounded away from 1. And this epsilon here, it's certainly the same for all words in the language. It's actually the same epsilon, and it depends only on R and Q. So it's fixed for the language or for the verifier V. If you think about this, and this is actually quite close to our goal, because this is another way of writing a gap problem for max CNF set, right? We start with some, okay, we still have to talk about how on earth we should get a PCP verifier with reasonable functions for any interesting problem. Set aside this, we can construct a formula that has this gap property. It's either 1, so the gap here would be 1, where actually we just have the single point fully satisfiable. And then there's a 1 minus epsilon here. And we have an instance of a gap problem for CNF set. And in the end, we will show that we can obtain such a verifier so that we can construct something interesting. Okay, let's do one step at a time. And since I'm running out of time, let's not waste more. We have to simulate this verifier in terms of a formula. And what we will do is we make pi the variables. So this pi has is a string of length L. And that will be the variables in our formula. Now note that this verifier requires us to provide it with some proof string, and we don't have it. So we better make that something that's open. So that's why we make it the variables. And we don't have to know the proof string here. But we can analyze the verifier. Okay, maybe I was a bit quick in concluding that we can actually give an algorithm here. These are the variables. And now for each random bit string, row, which is a random bit string of this length R, we read a certain, we read a few bits in the proof, and let's write these as Q of row 1 up to pi Q of row small q, because we read only Q bits in the proof string. And now we have to analyze the verifier. So the point is, if we have x and pi and row fixed. All that v does only depends on these q bits. And its output is 0 or 1. So it's essentially a Boolean function of q variables. Okay? And now this step is actually a bit of a black box. We somehow have to analyze this verifier, and I think this is not something we can do algorithmically very easily. Let's leave it like we can construct. But this is also not something we have to do as an algorithm. It's something you're given a specific proof system, and then you construct formulas. Now for any such fixed pair of input and row, there will be a certain pattern of these q variables that makes the verifier reject. So let's call that B. So that if this pi q of row, so these q bits are exactly B, V rejects on these inputs. Then we will add one clause to our formula. Namely, the clause that encodes that exactly this happens, but the negation of this. So intuitively, we would like to have phi of x encode the fact that the verifier accepts. And for that, we have to exclude all the proof strings that make it reject. The point is that we have to still take into account that there's randomness, which our formula doesn't have. So this clause can be written as follows. It's for all the bits in the pattern that are 0, we require that the variable that corresponds to that position that is read is true. So one of those is true. That means that it's not 0, so the pattern is not there. Or any of the positions where we have a 1 is not set. Oh, that's a row. Q of row should be these positions. Okay. So that's just the encoding in an ordinary CNF clause that we don't have this pattern at these specific positions. Okay, that's the types of clauses that we get. And we do this for all rows, so for all random strings, for all random bit strings that our algorithm can have, and for all the patterns where it rejects. So there's a large AND in front of this that goes over all rows and over all B's. And again, this is, the notation is a bit sloppy. But this is our formula phi of x. And this now only indirectly depends on x via the analysis of the verifier. So it's a purely existential thing at this moment. So the number of clauses can be bounded because we have at most 2 to the r rows. And for each row, we can have at most 2 to the q patterns. We won't usually have all of these, but that's an upper bound. And in fact, this formula has the nice property that all the clauses have exactly q literals, which you could exploit. You can extend the results by using the usual tricks to make clauses shorter. You can can turn this formula into a 3-sat formula in the end. But that's more technical stuff that I'll just skip. Doesn't add a lot of interesting conclusions. So that's the number of clauses. And now we should also verify that the formula has this property, that it's satisfiable if the word is in the language, and that it has this bound on the fraction of clauses if not. So let's look at the case that x is in the language. Then we know that v has to accept on the correct proof, and on all others we don't really care. But this means there's one setting of the variables, namely the correct proof pi, so that the verifier never rejects, no matter how row the random bits are set. Okay? And that means that we actually don't have any such rejection patterns in that case. So the formula then is satisfiable. And the other part, if it's not satisfiable, then we know for every proof string, so for every assignment of the variables, we must reject with probability 1/2. So that means in terms of the bit strings row, of the row values, reject. So in terms of the clauses, that means we have a certain number of these b's, namely at least 1/2 2 to the r, because that's the number of different row strings. And for half of these, we have to have a rejection. So this is again very implicit because we don't know what the variables are and how it will reject in this case. But there's a certain number of rejection cases. And that means for every variable assignment, these clauses cannot be satisfied. And by the bound on the number of clauses, this 1 minus epsilon fraction is not fulfilled for an epsilon that's exactly this divided by the maximal number of clauses that we can have, which was this r plus 2 to the r, 2 to the q. And that's just canceling out the r, 2 to the minus q minus 1. Which, if q in the general case grows with n, means the gap is shrinking. So for this really to be helpful, we should actually have a small q, a constant q. And to have a formula that's of usable size, r should actually be logarithmic, or at least O of log. Then we would have a polynomial size formula. And the stunning fact is that this is really true, the class NP is characterized as exactly those languages that have some PCP system that uses a logarithmic number of random bits and a constant number of accesses to the proof. And one direction is easy. We already showed that this is contained in that by the simulation of a non-deterministic machine. And the other direction is a really deep result, because essentially it means that you find a very clever encoding of certificates so that you can check them with a large enough probability by only a constant number of bit inspections. And I think the current record is actually a 3 here. So you need 3 accesses to the proof string if you take the right construction, which is very involved and complicated, but in theory doable. Well, and what this means is that Q in the best case would actually be 3 here. So we have quite a generous gap. Let me see, Q3, that would be 1/8. I think this is actually the best you can prove for max 3 set. Okay, first of all, we haven't shown that. I only constructed a formula that is just C and F. It's actually Q, C, and F, but we haven't talked about what Q that really is in the direct case. But this means that we can't approximate max set to an arbitrary degree, because by this theorem, every NP language has a PCP verifier. And this verifier can be translated to a CNF formula with a gap. And that means if I could approximate max set with as good precision as I want, I can solve all of NP. I can decide all of NP. And in fact, using this, using the PCP theorem, so this is the most famous version. There's a whole zoo of theorems of this kind, which differ a bit in the details of what is used there. And if you have the one where Q is actually 3, then you get that max 3 set has no poly time. What was that in our? So okay, the stated result is this, where you have the approximation factor below 1. So I think for us it should be just 1 over that. It's a mess, because in the literature you always have either approximation ratios are always larger 1 or always smaller than 1, or depending on max and min we do one or the other. So it's really confusing to transform the results. So for max 3 set, the current knowledge is perfect. You can approximate it to 7 over 8 by a not extremely complicated algorithm. It's trivial if every clause contains exactly 3 different literals. Then you can just maybe not trivial. And you can show that no better algorithm exists. And then you can start showing with gap reduction starting from max 3 set that other problems are also hard. Unfortunately, most of these reductions use, again, expander graphs and other complicated instructions. So I didn't find a nice, easy one that directly starts with that. So we'll leave it with that. We can't approximate max set to arbitrary precision. And that's the starting point for a whole collection of results that shows for many problems that they are inapproximable, that they are not approximable better than certain constants. And you can lift the theory also to problems like set cover that don't even have a constant factor approximation. You can also show by more general PCP theorems that set cover doesn't have a sublogarithmic approximation factor. So there's a lot more to explore, but I think for this course we're fine with the results as it is. I find this, the PCP theorem, a nice part of theory because it connects randomization and approximation, and we've also found this connection with f-petas back to fixed parameter tractability and pseudo-polynomial algorithms, which shows you that all these things are in a weak sense connected. I mean, not always, but there's a lot of connections. And so this is a nice last topic for a lecture that deals with the strategies to deal with hard problems. Yeah, thanks for staying with me so long.